All right. Um, Hello, everyone. Welcome to another Common Lisp Study Group. I'm your host, Ram Vedam, with Atlanta Functional Programming. I'm making a special live stream of a continuation of what we were debugging earlier on the study group with relation to our CL4 series. As it turned out, there was a misunderstanding based on um, my reading of when to use a certain statement that I'm going to try and clear up here with relation to our current debugging exercise of our if-then statements. As it turns out, the book uh, implementation had a very specific definition of what it meant to be in immediate mode. Specifically, when creating metaprograms like the if statement, those are intended to be used only when you are compiling. That is, when you are generating new words that are in immediate mode and you use them in other metaprograms, then you'll be able to use them to create some complex logic. So in the case of our if and then statements, because we are trying to compile multiple of these words, that is, and specifically for if, not, branch if, and no op, and then no op, in order for this to actually run, it has to be in the target thread. That is the target word that you're actually creating. And we'll see something like this when we talk about implementing else, which we will do in a minute. This was a misunderstanding before. That means, though, that when you are not in compiling mode, that word will end up injecting its target thread, its fourth word thread as is, but it hasn't been compiled. It'll be immediately executed. And what that usually involves is it actually trying to compile stuff while it's executing. So you're attempting to essentially inject code for code generation in a place where what you really want to do is evaluation. This is why it wasn't working earlier in our particular example of the go forth, new forth, 4, 5, if, less than, if, hello, print, else, then, example. The reason for this is if and then have not yet been compiled. They are not words in our dictionary. They are meta words that will inject code into whatever code that you're trying to attempt. A better example of this is if we create an example called check condition. Check condition is a condition that will simply take in something, whatever is on the stack. If it's nil, it will do nothing. If it's true, then it will print yes. Okay, so you might think of this as being something that you could then use later on if you wanted to do like branching inside using branch if inside the code. Specifically, later on, if you ever wanted to, do more declarative like check conditions, you could certainly build something like this. So to give an example of this, let me clear my REPL. Let me go into this example here. Okay, and let me go and change some of this so that the grouped examples are next to each other. This, okay. And this should, oops, sorry. This here should do what we expect it to. Okay. So if we compile this check condition here, let's go ahead and create a new, go ahead and convert these guys. Let me move this around here. And then group the words for example later on. So we're going to create a new fourth interpreter with our standard library and these two additional functions. Print hello and check condition, although we're not going to use print hello for the time being. And what we're going to do is we're going to have two cases that we're going to try out. One is simply going to check to see if 4 is less than 5, and then print yes if it is, or 4 greater than 5, and check not. So the first time we try running this guy, you're going to see that it will go ahead and appropriately print yes, as we expect it to, because 4 is less than 5. If we try in running greater than here, you'll see that it compiles, but nothing gets printed. Well, that's correct, because of the fact that it's nil, so the branch if statement is going to jump to the then, and then has nothing in there, so it's going to not return anything. We'll see the same thing if we end up going back to the absolute value section. Let's show you what absolute value looks like, which we have defined somewhere. 1 second. ABS name. Yes. So if you recall our absolute value function here, which has a simple duplication of the function, duplication of the value, and it does a check condition to see if it's less than 0, and if it is, or negate it, which will give you the absolute value of the function. Otherwise, it will just return whatever is on the stack. It won't manipulate the actual stack. So when we run this with -5, we will see, as expected, that it's going to go ahead and return a 5, as we expect. Now, if we go ahead and run our stack here, let's see what's in our stack now. We'll see that there's nothing in the stack right now. It's just going to go ahead and it pops it off when it goes and prints it. If we go and run 5 on absolute value, you will see again that 5 is just going to be printed, because what? It doesn't get manipulated. It's still going to be on the P stack. It's not getting negated. It's just going to skip it off and continue execution. That's kind of what we were expecting. Now, the point of this exercise that we've been going through is this is if the if statement and the if-then pair is nothing more than your first metaprogram. It's the first metaprogram that we've written in Forth. So let's see what we've done up until now these past few weeks. We've essentially wrote our own Forth interpreter. We essentially wrote the primitives for Forth metaprogramming in compile in here. Okay, compile, again, is the one that's actually setting up the compilation chain in the target thread that we're defining. And here is simply taking the last instruction of that thread and sticking it in the parameter stack. Okay, so that's necessary when you are building up these tiny metaprograms. Both of these are required to actually go ahead and do what equivalently in Lisp is doing with def macro and using macros to actually go do metaprogramming in Forth. So we're going to go ahead and leverage this to actually go and build a couple of more statements in our language. One is going to be, again, these are actual, you can think of these as being additional words for metaprogramming. So I'm going to go ahead and label this for folks who are going to be dealing with this, so that they don't make the same mistake I did, which is this section here, the if statement, the then statement, and some of the additional programs that are built on top of that. That's going to be our words for metaprogramming in Forth. I'm going to go ahead and label this section so folks who are watching this, or who's going to look at the code in on GitHub, you guys can certainly go ahead and play around with this without having the same mistakes that I did, mainly dealing with issues of trying to run stuff in evaluation mode when they only can be used in compilation mode. And again, the difference between compilation mode and evaluation mode, where things are getting executed, is stuff that we defined earlier. We created a word called compile, and compile is actually when it's in immediate mode, and that happens when you use the left curly brace, as you saw when we were defining the create statement here in the library. And this create and postpone is needed to be able to go in and out of immediate mode. So let's go ahead and add our else statement. Our else statement here is going to be just simply another meta program. We're going to first compile true onto the stack, and then what we'll do is we're going to compile branch if. And branch if is going to go and change the conditional. Again, although if and else are two different syntaxes in terms of defining a control flow, essentially they are nested ifs. If you're thinking about it as single conditionals, and one is just a true branch and one is the false branch. The one thing to recognize though is the role of the control stack that we've been using up until now, which is actually the parameter stack that's inside of our fourth interpreter. This control stack is very, very important in the compilation process of new words, because it allows our if statements and our else's to be nested accordingly. So as long as each if statement is associated with the corresponding den in our fourth program, it can jump out of a particular nesting and go up in terms of the scope. This is one way of not having to deal with creating block scoping and block structured scoping that's commonly used in languages like C, C++, and other languages where, although there's a stack and a heap, you don't have direct access to those data structures where you can manipulate the language at compilation time or at runtime. So we're going to go ahead and use this this branch if that we've defined already, and we're going to define our else statement as the following. And again, if some of this may look familiar for folks who have tried to expand, as we saw in earlier episodes, the if and then. The if and then together create this compile no op here swap kind of like logic. So whereas before they were separated, we're not separating them in the case of else because of the fact that else is kind of like the final branch, if you will, the final logic that that the then will then associate with when it's moving on. So this is our else statement. Let me just make sure that I didn't miss anything, and then we can go through it. Compile branch if, no op, here swap, compile no op, here swap, and then store the final instruction. Yes. So this is the definition of else in our code. This has defined in let over lambda. Again, the code is freely available on the let over lambda site. If you guys just want to follow through, some adjustments that have been made mainly related to dealing with syntax highlighting with our editor. And for some reason, I see syntax enabled is not actually, it's not turning on here as it did before. So, okay, that's something that I'm going to have to think about and look into. The difference is mainly between the code that's defined in let over lambda and the stuff that we're here is we've been more complete in terms of the word names instead of short word names, just so that we could take advantage of do Emacs and space Emacs's ability to highlight some of these macros that we've created up until now. So, how does this look like in code? Well, we can actually leverage this else statement to create a word that defines whether or not something is can be modded by 2. Well, what does that? What is it? What does that mean? Well, up until that just means checking to see if it's even or not. Earlier in a past episode, you may have remembered or recalled that we've actually defined this, whether or not something's even or not. We have a predicate in common list that we pulled into our fourth standard library called evenp. If you recall, this was part of our use of the fourth unitary word definer, as I show right here. This is basically a predicate that just takes a number, and if it's true or not, it will, it'll print true if it's available, if it's even, and if it isn't, it will print nil. So if we see here, this is the common Lisp implementation. If it is odd, it'll print nil. We're using this inside of our CL4 interpreter to define if else then. Okay, mod 2. Notice we are not actually making this word. Notice we are not actually making this word like absolute value an immediate word. It is not a word that needs to be immediate. It's going to be compiled and executed when we're evaluating stuff. Let's see how this might be leveraged. We go ahead and crap. Okay, let me go and first define our read table. All right, now we got it. Let's go and go down to where we defined our little guy with examples. In fact, let me go ahead and do this, because now that we kind of corrected everything, we can actually go through and do this. Oh, oops. Oops. Let's go ahead and do this. Boom. Boom. This may not be necessary anymore because this code won't work unless we use check condition. And this may not work. And for folks who are interested, this code will be on my branch for a bit before the else statement additions branch on the GitHub repository. It will be eventually merged into master. I'm going to do a little bit of cleanup in this branch before I go and merge it up. For folks who want to wait maybe until tomorrow before pulling in the changes, that would be most appreciated. That way I can actually clean this up and you guys don't have to go through the exercise of having to deal with all this commented code. A lot of this, though, is basically just for examples and stuff that we've gone through throughout our tutorials thus far. I'm just going ahead and some of those error messages were related to the issue of using here has a naked primitive versus here has a is a normal primitive that sets up the program counter after each iteration. So let me just do this one more time. I'm going to go ahead and check, see all is good. Hopefully where equivalent is unbound. Wait. Got to take a look at that very quickly. Square is not found. 9. So this stuff here. Go ahead and do that. Go and clean up a couple things here in real time. And where is that happening? Square cortex. Look at. Okay, no matter. We will deal with this, and I will make sure that that code gets corrected accordingly. Okay. Just comment this piece out for right now. Go ahead and do this up to here. Let's see what happens. Almost. Oh. Just realized I had a break statement here. All right. And for folks who are interested about line 463, I will. There's a way to step through code, including executing top-level metaprograms using the step function that's inside Common Lisp. It will hook into the debugger of the Lisp that you're leveraging. And you get some options. I will cover that in another episode, although right now it is not needed, because I think we've covered most of that. I'm going to just do one more restart here, just to make sure that I didn't. Good. Move forth is unbound. Okay, got it. I know what to do. This is here, go here, put this at the bottom of our definitions. And the reason why I'm putting it at the very bottom is so that as we add stuff and recompile, it is correctly in the interpret. It gets to all the latest changes. So let me do one more restart here. Turned on is unbound. So far so good, it's still compiling. Good. All right. So let me go ahead and check this guy in for folks who are looking at the else statements edition. Fixed. Added. Statement. Okay, so let's see how this works. So just recall to see if a new addition is in the work. I mean, a new word correctly is inside our dictionary. We can use our with Pandoric, grab the dictionary for the new fourth interpreter that we just defined. And then what we could do is we can use print fourth lookup, the word that we're looking for, which is mod 2, and it's in our dictionary. Is it in our dictionary? And it is in our dictionary. Now, for those who are watching, you may be wondering, well, Ram, what the heck did you just show me there? Because that just went by really fast. Well, that's because of the fact that recall our dictionary is a linked list, so it has all the stuff there. So it has it's linked into the list. So you're getting all the current word and all its previous words that it's hooked up to, all the way up to the innermost word that's been added to the dictionary. With mod 2, of course, being at the top of the list. Let's see how mod 2 is used. So let's go ahead and clear the REPL here. And let's go ahead and show some usages of mod 2. Okay. One example of this is if we do go forth, and we do for mod 2. Okay, I'm not going to print anything right now. We're just going to see what's on the P stack. All right, that is our parameter stack. Okay. I will also at some point turn on logging to show you what's happening in terms of the execution style. But for now, if we go and look at the P stack here, you will see that as we expected, and let's show the use of mod 2 here. If you see and if you recall what our mod 2 function is supposed to do, it checks to see if it's even. If it's even, it'll go ahead and set it to 0. If it's odd, it will be set to 1. Right? So let's go and try then 5, instead of 4, which obviously is going to be an odd number. You could certainly try even 1. Okay, for example. If we look at the P stack again, you're going to see 1 and 0 being available on the P stack. Why? Because we just passed in 4. We went ahead and did mod 2 on it. Clearly, it went into the true branch because it's even. And then 1 is going to be sent in for odd. This is all pretty basic stuff, right? What this allows us to do is we can now leverage mod 2 in code to deal with modulus and check to see if things are even or not, and only use bit flags for some of those changes. Nothing spectacular there. Nothing really too complicated. But the other two things that we need to add here is features for looping. But before we do that, there is a couple of things that we need to talk about in terms of else. Else, as you can see, is it compiles into an unconditional branch to the actual then, if you recall, is merely because, as you saw right here, the way the else is structured, it is a branch to the actual that's set up so that if then is available, we could then go in and we can actually um, move into the branch. It's an unconditional branch of terminating then, and then if there are subsequent branches, we can skip the false tertiary or alternate branches and just go straight to the else. Else makes use of whatever is left on the stack by if to replace the no ops with the start of the code block that's represented by the else. This has been particularly important because, as you recall, we are in cons threaded mode. And cons threaded mode means that until something gets evaluated, we don't know necessarily its memory location. So these no ops are necessary inside the compilation code because this is effectively telling Lisp, hey Lisp, could you go ahead and construct some memory for me for an instruction that I'm going to end up executing later on. So this matches kind of what we've been seeing with if and then, so I'm not going to go too much in depth in here. The one thing that I wanted to mention is that at the end of the day, without the control stack, a lot of this is impossible to actually, well, it'll be a little bit more complicated to actually go and implement, primarily in that you're going to have to create either a separate stack or what have you. Given that we're using the same stack, the P stack, to leverage this, we have some great advantages. One thing to note about our conditionals that we've talked about so far, most of them are all implemented in a tail call fashion. And there's some advantage of this because it allows us to use the same technique to implement essentially like accumulation style constructs and iteration constructs, including loop. We've talked about, I mentioned loop earlier, but loop isn't the actual keyword in Forth. In Forth, the keywords to talk about when you're talking about looping words or iterating a particular set of code multiple times is begin and again. The two words together provide a simple infinite loop, and they are essentially the iterative equivalents to our if-then pair in order to deal with nesting. Now, the main difference between our begin and end words and the if and then is the meaning of the address that's saved on the control stack. The meaning of the address on the control stack when you're dealing with begin and end is corresponding to like a branch. Okay, it's corresponding to essentially something that we jump to, but it's not necessarily a storageable address that we're going to use later on, like our no ops. Let's see how we implement this. It's actually a pretty simple thing that we saw before. You can almost see that this looks very similar to our then clause, but you will see a subtle difference. One in the sense that it matches it does not actually swap anything, and store any addresses once an execution is happening. And it's because it's not necessary. It's going to be used, that no op is going to be used later on when you look at the again statement. So let's see what happens when we use again. So if that's begin, well then what's again? Again is just basically like our else statements before, but it looks more like the opposite of our if. Okay. Instead of, and I'll show you the differences between the if statement and this one here in just a minute. Excuse me. I was just about to have a sneeze. All right. So immediate. Okay. Let's go ahead and compile this. Once again, I forgot to add my read table. Let me do this again. We are good. Square. Okay, square is defined as a macro. Make it defined as a function. Here we go. That's right. Compile no warnings. Let me just make sure that's the case one more time. Compile no warnings. Excellent. All right, let's get back to our begin and end statement. I think the best way to actually explain what's going on here with begin and end is through an example. Let's go and define a word that uses this looping construct that we've just defined, okay? Again, remember, these are immediate words, which means you cannot use them without them being within a curly brace pair. Just like before, I'm kind of reiterating this now because I made this mistake, and I'm trying to kind of remind myself for future people who are watching this, not to mention future versions of me who might go back and review this. So here, we've defined our new fourth, which now has our stack, and you can actually probably go and do this here. Let me go ahead and make this into a function so I can not have to write all this code all the time. Lookup word. W, so I can actually quote W. Okay. Lookup word mod 2. Mod 2's unbound. Dang it, I can't do that. Okay, fine. Let's do this way then. I was hoping that I can actually get that in there without having to create another macro, but I'll just go ahead and use it this way. So what was I looking for? Begin. Oops. There we go. Let's see if again is there. And it is. All right. So let's go ahead and create a new direction called that simply takes whatever is available on the stack, and we're going to just loop until we go down to 1. So we'll find a number on the stack, and it will loop until it goes down to 1. We'll call it countdown. Okay, this is what's defined in the book as an example of using this looping. We're just going to go ahead and leverage this guy. Okay, what is, so obviously we need begin and again in the same area. All right, What are we doing in between? Well, we're going to first duplicate the guy, the value that's there. We're going to go and then check to see if it's less than 1. If it's less than 1, we're just going to go ahead and drop the value and exit. Otherwise, we're going to go ahead and print the value and then decrement it and then loop back. All right, so this is going to print every number until it hits 1. So let's go ahead and do that until it hits 0. So let's go and check out the use of countdown after we compile it. And we're going to make a separate command here so that way we separate the usage of the words from the actual thing. Although I could tell you right now, for folks who are coming in, who are like wondering why I'm doing that, I could simply write code like this, but I'm sure most folks who are looking at this at home are wondering what is going on. This is just simply me defining a function called countdown and then using it. Okay. As you can see here, all this is doing now is it starts the loop. It does exactly what we're going through. We're checking to see if it's there. If it's not, we'll duplicate it. Otherwise, it will decrement the value and then go again and loop it. So, and if it's less than, once it becomes 0, it'll drop the 0 and exit. Okay, so now what that means is we look at our P stack. Our P stack and our R stack are both nil. Let's actually go and debug this for a second here. And I'm not talking about necessarily debugging, but we're going to actually go ahead and look at the execution of the code when we run this command, shall we? So we go ahead and we run it. Let's go to the top. Okay, let me go ahead and clear this REPL. Oh, thank you. My apologies right now. For some reason, doMeMax is, whenever the buffer gets a certain size, doMeMax just starts going crazy. I have to set the undo outer limit, but I haven't had a chance to. Give me a moment. There we go. Okay, this is clearly causing some trouble. Let me go ahead and restart my Lisp. I don't think it liked the fact that I was attempting to turn on debugging after the word was added. So let me go ahead and separate these two to make things a little bit more easier for us, shall we? Okay. Fourth. All right. Yeah. Again. All right. Good. Okay. Clear. Okay, you can just see that that's working now. Let's go ahead and turn on logging. On true. So, in the beginning. Ooh. I didn't realize I forgot to drop those. 1 second. Print. Just make this print so that way later on when I go and redefine them. This way the parameter stack is always nil. I like the fact that it's kind of empty whenever you do this. Okay. Thank you. Okay. That took way too long. 1 second. Well, I appreciate those of you who are joining the live stream. I'm glad to have you with us. I'm here on this special definitive version of the Common Lisp Study Group. Okay. For some reason, it is dumping out a bunch of. Okay, I see what the problem is. This is because of the fact that this is a loop, so it's just constantly. Thank you. So this is I'm gonna have to go with a smaller number of iterations just for the purposes of our discussion. Otherwise, this is going to take a little bit of time. Clear this. Thank you. Restart. Do this again. Before I do that, let's go and turn down this. So it's going to only loop once. It doesn't make much sense, but for our purposes, this will be much more simpler. We will go ahead and, in fact, comment this out when we're loading, so we don't need to worry about it. There we go. Thank you. Thank you. That's right. Okay. Set package. Fourth. Get this to my read tables so that I can actually use this. And let's increase this size so that folks here on our stream can actually watch. All right. And folks who are watching, if the font size is too small, please post messages either if you're watching afterwards, please post it in the comments and YouTube channel and the YouTube video. If it's during the live stream, by all means, if I forget, please post it. I'm watching the chat to make sure that things are okay. Okay, so let's go back to what we were going to be doing earlier, which is All right. There we go. All right. So let's go ahead and comment this guy out. This, all right. Okay. First, we're going to turn on logging. Then we're going to run one iteration of this guy. It's going to take a minute because of the number of instructions that are being executed, but we just let this run for just once. It should just stop itself. Well, let me do something else here. I'm going to not print out the dictionary like I was doing before. This is related to the program counter being set up. And right now, we don't need the program counter. Let me do this. Okay. Program counter. Okay. Go ahead and do this. Okay. Okay. Let me get the other program counter here. This is setting up the program counter. Okay, this should all work. Oh, right. I forgot to compile it. Load this guy into this new image. Shoot. This again. Okay. This must be related to the fact that I also need to do this one. Okay. I need to stack. Okay, I think I've done all I need to. Let's go ahead and just make sure I comment out this particular piece of code for the time being again. Okay. Sorry, for some reason the buffer font sizes keep on getting messed up. Okay, so I think I loaded this all correctly. So let me go ahead and set my package for okay, go down here. We have it. Okay, I see what the problem is. Okay, long story short, since we're pushing closures onto the parameter stack, and those closures themselves have multiple nestings, the structure of this is too big for the buffer to actually go and handle. So the one way of actually doing that is to write a scribble out and then make sure that we can actually grab that information at some point. Okay, I'm going to go ahead and turn this guy off because this is kind of like delaying certain things. This way we can actually go on to bigger and better things. So, okay. All right. Since this is already turned off, I don't need to actually do that. And do this. Okay. Okay. So let's move on. So let's go and review this code that we just wrote here again. So if we're paying close attention to this, you're noticing that that this is almost like a nested if, because the if and exit is nested inside of the begin and again, and because of the control stack, we're able to nest any control structures with respect to or that respect the stack operations, the push and pop operations. Typically, when you are dealing with scope, this is one way of actually implementing scoping. You can, when you're scoping something, and it's essentially adding a new stack frame that you could then, add local variables to, and then you could pop those guys off. And the same idea applies here. This is regardless of language. If you're dealing with scoping, the scope of where your variables are located is going to be respecting the stack that you are manipulating to keep track of those variables. What do we mean, though, by respecting the stack and its operation? That means the control structure that we're defining should avoid popping values that it doesn't own or it didn't push into it, right? So when I say ownership with respect to the stack, if you're within the scope of your stack, okay, you're only popping and pushing values that you have access to. You're not popping and pushing values that you shouldn't have access to, okay, and you don't have access to. So as long as the control stack is popping values that it pushed, and it leaves any extra values on the stack that is scoped to the outer stack, in which invoked that new stack frame. Then it's respecting the stack semantics, and it is a perfectly acceptable control structure to nest. Now, this is also kind of like similar to when we're talking about Lisp macros and the idea of not violating referential transparency. So when a variable is assigned, we don't necessarily assign to it, but instead it is something that we don't necessarily modify it after it's been initially assigned, is what I mean. It's always treated as a constant, just like we try not to violate that when we're constructing Lisp macros. And fourth, this stack respect, or this stack violation, or avoiding stack violation when compiling, is very, very necessary when you're dealing with metaprogramming inside of fourth. To give another example, we're going to not deal with, excuse me, we're going to actually not have this exit code that we had before. We're going to create another countdown example. And we're going to not use exit to escape from the loop. Instead, what we're going to do is we're going to go into compilation mode and swap the pointers placed by the if statement and the begin statement, so that the then that matches the if and the again can be used in out of order execution, in out of order style. So let's try it. Let's try and show what this is. This is kind of weird. I myself have been trying to understand this example. So hopefully those of you who are online who are watching this stream, you could take a look at the code and give me your thoughts on how this might go down. Example of swapping pointers made by begin and if, so that again and then are run out of order. This is kind of a hacky example, and by hacky I mean it's something that looks like something that shouldn't be valid fourth, but is perfectly valid fourth. So let's just go ahead and do this. We have our begin and again. Okay. All right. And then we're going to go ahead and add a then here afterwards. All right. And again, you're seeing that what we're doing is we are going out of our way to kind of manipulate the pointers, the memory address that we're executing and when we should execute them. So here we're going to go ahead and say if it's greater than or equal to 1, then it's not if then double. Why are we doing that? Okay. Then what are we doing? We are duplicating the value, and we're going to print it, and then we're going to decrement the value, and then what we'll do is we're going to go ahead and swap the value out. And again, recall the left square bracket represents getting out of compilation mode or getting out of immediate mode, and the right compilation bracket means that we're going into compilation mode. Okay, we're going into immediate mode. Okay, I know it sounds backwards, but that is how it is defined in our fourth. That is how it's defined in the CL fourth. That is defined in let over lambda. and it's because we're avoiding certain things that are inside and predefined in Common Lisp itself. So my apologies if that's going to be a little confusing when you're reading through it, but if you read it enough times, you will understand and you will drill it into memory. So we're going to go ahead and set this up, and otherwise what we're going to do is we're swapping their pointers, and then we're going to at this point swap their pointers. We're going to call again, and then we're going to drop it. So when is this swap actually going to happen then? Well, this swap is actually going to happen every time that we do this duplicate. All right. And if this is not true, then it's going to just skip over all this code, all right, and then go into the drop section. So it's going to drop whatever is currently on the stack. We're going to call this, the book calls this guy Countdown for the Hackers. I will go ahead and name it accordingly in honor of Doug Hoyt's example, because I think it's a very good example. Hackers. Alright. And we're going to compile this guy, and we're going to see what happens when we run this. When we run this here, you might be thinking, is this actually going to work? And sure enough, it does. Why? Well, it's happening because of how if and then are structured. Remember, if is behind the scenes keeping track of the console of the condition that it needs to execute, of the instruction that it needs to execute if the condition that's available on the stack is set to true. Remember, that is what branch if does. So if that's the case, whatever manipulates that memory address, that is the memory address that it's going to go ahead and jump to. So if we swap those locations, then certainly whatever is the previous memory address, which is going to be the if address, okay, whether the condition is true, that's going to be swapped with whatever begin is. And we'll just keep running that code and again until we hit the nil condition. Then we automatically jump to then, and we'll drop whatever is available on the P stack. Now, did it actually drop on the P stack is probably a good question to ask. Well, let's look at this, shall we? Let me go ahead and do this, and let's go and do that. Okay. Whoa, that actually worked, right? Well, is there a way to actually now see this when it's being executed? Let's see what happens if we think about adding some code to, oops, sorry. P stack is this way. Is there a way to turned on? Let's see what else can we turn off? Force handle. Let's see if we could oops, that would mean this. this entire code piece can actually get taken out along with this. Actually, I have a better idea. Instead of doing this craziness, we can actually just leverage okay. We can actually just leverage stepping through the code when we execute something. Let's see here. Let me see if this will actually work, fellows who are watching. Hopefully this will all go well. No, did not work the way I expected. Okay. I was hoping that we'd be able to interrupt the execution at some point. But since we didn't include anything like that in our fourth interpreter, it is unfortunately not possible. That's okay. I think we can stop here about that discussion. And let me just make one final point here. And let's review actually this code. What is this code actually doing? So, what is the role of again here? The code that again is compiling, okay? Which again, if you recall, begin and again are like if and then. Again is basically pointing to begin and to specify, okay, you need to go to a next iteration. But the only time this is going to be compiled, okay, is if it's going to be executed is if the condition, whether or not x is greater than or equal to 1, is valid. So it's within the if condition itself, okay? You can't do this in other languages at all. You can't actually try and make it so that this is kind of like an implicit a preemptive exit of an execution of some code because the condition is structured in such a way that it could preemptively exit. And this is without any sort of preemption. You're just using a simple conditional saying, hey, can I still run this? Okay, I'll keep going and looping. And if not, I'll just go ahead and exit out. This is how kind of like how while is implemented in a lot of languages. So without getting further on this, I'm just going to iterate that very few languages, and this is something that the book stresses if you guys reread Let over Lambda. Very few other languages allow you this kind of access to the compiler. And this is Hoyt, labeling anything that can't implement fourth and has flub, just like we've been labeling blub, the blub paradox for blub languages for Lispers. But because of this kind of freedom that's available, where we can mix and match accordingly, and everything kind of works out correctly, fourth programmers have just as much, or even are more accustomed to doing very advanced macro combination and macro combining than most other Lisp programmers. So this kind of goes against what he was talking about in the book, but it does actually it does mention that although the Lisp code that he wrote in the book, in the Let over Lambda book, uses macro combination techniques regularly, they're not nearly um, they're not they're not frequently they're not used as frequently as using these kinds of fourth combinations in production level fourth code. So you might see these kinds of settings in production level fourth code, but the kind of combinations and macro techniques that we were talking about throughout this book and throughout this tutorial, this case study of writing a fourth interpreter, a lot of those techniques aren't really used in production level code. Some of those, just to review here, again, I'd encourage you to go watch some of our past episodes on Common Lisp Study Group for this information. Include anaphoric macros, or advanced uses of anaphoric macros, Pandoric macros, advanced uses of Pandoric macros, when and where to use compiler macros, when and where to use reader macros, although reader macros have their own problems, as you saw throughout these broadcasts that we were using. In particular, if you are going to lever using reader macros in Lisp, you would have to make sure that you set the read tables accordingly and reset them after you're done. Otherwise, you're messing the image up for standard readers that are available. Even with the use of named read tables, as you saw earlier, I'm using it in production in my code, but it doesn't. It's not readily available sometimes when you are loading up your Lisp image, although it will be readily available as you're loading up your Lisp image. So when you load it up, those read tables will be available, but once you're done with reading whatever that requires those read tables, it usually gets reset. This is standard bookkeeping that you need to follow in the Lisp world, but in the fourth world, a lot of that doesn't necessarily apply, because fourth a lot gives you more control over some of those stack structures that you can respect. And as you saw here throughout these examples and throughout this section, a lot of fourth's nuances, although a bit confusing at first when you are coming in from any language, regardless if it's Lisp or not. It gives you more power and more freedom to write some of your stuff from lower levels and make things a little bit more cleaner over time. So I'm going to leave the very last section on this, and this is us actually implementing Lisp in fourth till next week. I really wanted to clear up some of this final section so that we can get into the meat of the matter, which is implementing our Lisp in fourth in Lisp. So we're going full circle, and that is the final section. Now, we're not going to implement a full Lisp, we're not implementing a full common Lisp, but we are going to be implementing a good portion of it, so that you can understand that now once you're at this level, you can build up your languages even further. So until next time, thank you all that are joining for the second video that I created on this Saturday, August 8th. I appreciate those of you who have joined me for this debugging session. And my apologies for some of the confusion that has been happening throughout these weeks. I hope I cleared those up. I certainly cleared some confusion I had. It's been a journey, but if there are questions, feel free to post them. I will address them accordingly, and I'll stay on for a few minutes if there are folks who want to ask questions. And I'm going to mention now that all the code that I have just put on this broadcast and illustrated in this broadcast is entirely available in the else statement additions branch um, in uh, the Atlanta FP GitHub. Um, if you guys wait until tomorrow, I will go ahead and merge this stuff into master, so that way this is you folks who are just pulling in these changes can just pull from master instead. Thank you, I appreciate it. I'll still stay on for a few minutes for questions if there are any. All right, if there are no questions happening, I will see you guys next week, and have a great